We consider the problem of adapting robot manipulation to partially observable environments. Unobserved obstacles can cause task execution to fail if planning methods are missing crucial information such as obstacle geometries. To address this, we introduce constraint-obeying Gaussian implicit surfaces, or COGIS. COGIS uses a Gaussian process implicit surface, or GPIS, to compute an uncertainty-aware estimate of obstacle geometries. We do this through two contributions. We estimate contacts with the environment online using information from state tracking, vision, and predictions from nominal dynamics. We then refine these estimated contacts by ensuring the estimated geometry satisfies user-provided constraints. We estimate contacts by comparing the dynamics prediction for a transition with the observed next state, and detect contact if we observe a lack of motion relative to what we expect under nominal dynamics, as shown in the red transition in Figure A. We use limited visual data, if available, through a depth image of the scene. Visual information can prevent false positive contacts from being added to the GPIS dataset. An example is shown in Figure B, where part of a cable being in contact with the obstacle could lead to contacts being estimated along the full length of the cable if vision were not used. Importantly, we do not assume access to tactile sensing. This is necessary when manipulating objects like a cable where there is no tactile sensing along its length. We fit a GPIS using a set of estimated interior and exterior points. Interior points are points in 3D space with negative labels, while exterior points have positive labels. The GPIS then interpolates a zero-level set between these points. For each contact we estimate, we compute a pair of points, with the visited state being exterior and the predicted next state being interior. Due to heuristics in estimating contacts and noise in state estimation and dynamics, estimated obstacle geometries may violate assumptions about the task. A key contribution of COGIS is refining the estimated contacts and ensuring constraint satisfaction by removing points from the GPIS dataset that cause constraint violation. We formulate an integer optimization problem solved with CMAES with margin, or CMAWM, a particle-based optimization method. We compute a binary value for each point in the dataset, where a value of 0 results in the data point being removed. We construct an objective for CMAWM that minimizes the change in the surface as a result of the optimization while ensuring constraint satisfaction. In Figure A, the surface violates a constraint requiring the region where the goal is to be connected to the outside region. We make the surface satisfy the constraint by removing the data point above the goal. CMAWM does not require its objective function to be differentiable or convex, allowing us to incorporate constraint violation in the CMAWM objective and guarantee constraint satisfaction by evaluating samples from the distribution fit by CMA. Please see the paper for more details on the optimization. We evaluate our method on peg and hole and deformable object manipulation tasks. We use Model Predictive Path Integral Control, or MPPI, for our MPC controller. We include cost terms that minimize distance to the goal while avoiding collision with the surface. We also minimize the magnitude of the control input and use the variance in the GPIS prediction as an exploration signal. Please see the paper for more details on the controller setup. For the peg and hole tasks, no obstacle geometries are known a priori, and there is no visual sensing. In the PEGU environment specifically, the narrow gap can result in an estimated surface, shown here in purple, that encompasses the goal. This leads to no collision-free paths to the goal existing, as can be seen on the left. For these tasks, we constrain the surface to avoid this. A result from the full method that ensures constraint satisfaction is shown on the right. As shown, spurious interior points that result in constraint violation are removed, allowing task completion. We also evaluate our method on two other peg and hole tasks with different obstacle geometries, showing generalization to different obstacle configurations. In this simulated cable manipulation experiment, a 16-DOF bimanual robot removes a cable from under a hook and navigates its center to the green goal region. There is a high degree of occlusion caused by the barrier in between the robot and the body of the hook. This can result in the cable state estimate penetrating the surface estimate, which can interfere with our controller that seeks to avoid the surface. We constrain the surface to avoid penetration. We use a vision-based estimate of the cable state for planning, shown in red. While this leads to state estimation error due to occlusion, COGIS is still able to complete the task successfully. Data are added to the GPIS when contact is estimated or if a local minimum in the cost function is detected through low motion of the cable. As we use the uncertainty in the GPIS prediction in our cost, adding the local minimum alters the cost landscape. A local minimum can arise due to the relative balancing of the different cost terms. Altering the exploration cost landscape through adding data offers a simple way to address this issue. We perform a cable manipulation experiment in the real world, where the robot navigates the end of a cable to a power strip. The clamp is partially occluded, motivating the surface fitting. We use a similar penetration-based constraint in this experiment. The cable makes contact with the occluded handle of the clamp, after which the robot is able to avoid getting stuck on the obstacle and completes the task. To conclude, we showed that our method enables adaptation of manipulation to partially observable environments with a priori unknown obstacles through online contact estimation. By refining these contacts using arbitrary constraints, we can improve the quality of the learnt model and improve task performance. This enables us to succeed on both low-dimensional tasks, like the peg and hold tasks, and high-dimensional tasks, like deformable object manipulation.